All right. We got through most of lecture 7, but we left one thing hanging. So let's jump right there. We were on the big boss, and I added one more level to lecture 7 to play with. We want to show that the reciprocal of a sequence converges to where it should. So let's get this over here. Of course, it's going to crash. And this over here. Actually, let's just state the theorem. The theorem, please. The theorem is if A converges to L and L is not equal to 0, then 1 over A converges to 1 over L. That's the idea. Okay? So let's do part A is scratch work. Let's try to be systematic about it. Scratch work. Of course, the key thing when we're done with all of our manipulations is that 1 over A minus 1 over AN minus 1 over L needs to be less than epsilon. This is what we want. This is what we want. This is our goal. How do we get there? Okay, let's do a little bit of algebra. So this is L minus AN over AN times L. It needs to be less than epsilon. So again, this is our goal. Our new goal, if we're keeping track of goal states. You can just write for yourself, scratch work, goal. And then what? Well, we can assume that AN minus L is less than something. I'll just call it delta. We can make it as small as we like by making n large. And I don't know what that delta is yet. And so what's the idea? This is after making n large. After making n large. John?
To try to not greatly manipulate A and L less than delta to look like 1 over or L minus A over A.
Yes, exactly. We want to manipulate this. The problem is there's something that's changing with n sitting in here. Suhas.
Equate A of n constant like maybe L over 2 or something like that.
Exactly. We proved last time, eventually, A of n is at least absolute value of L over 2. That was our theorem from last time. Okay? So after taking n maybe even larger, we can assume this. And if we have that, then our goal would be to prove, I'll replace this denominator by something even smaller, which will make the whole thing even bigger. And if I can prove that upper bound for this bigger quantity, I get it for the smaller quantity. So this is L over 2 times L. And then I'll flip these around because I'm a human being. Okay, so that's our goal. And that suggests a value of epsilon. So delta, meaning the epsilon that we stick into the limit formula, should be what? Like you. All that stuff moved over. Epsilon times L squared over 2. Okay, epsilon L squared over 2. If we have that upper bound for this, then we get the desired hypothesis. That's the scratch work. That's the beginning of just laying out the ideas of the proof. Now let's write out a formal proof. And then we'll put the formal proof into the computer, check that everything works out. Then at the end, we'll write out a proper natural language proof. Okay? All right. So again, what do we have? We have A to L or something. Oh, come on. Actually, you can still see, even though it broke, you can still see everything that's going on. It's called A to L. Okay, so I'm going to write it here. Okay, so we have things like A to L, which is that A converges to L. We have something called L NE 0. I don't know. I keep going back and forth between whether it's convenient to name things descriptively or just HL will do for now, especially because once we start specializing, they don't say what they used to say before, and now, you're just carrying things around, whatever. We have that B is, I'll just write it. It's called B I'll write it. B inv A, I guess that makes sense, which is that B is equal to 1 over A. And then our goal, this turnstile, is that B goes to 1 over L. Okay, so formal proof, step 1. Oh, you got one more on the ground. Okay, step 1. I lost everybody. We need to show that B converges to 1 over L. Thank you. Intro, give me an epsilon. Yeah. Intro, epsilon and H epsilon. H epsilon, of course, is that epsilon is positive. Okay, what value? Yeah, what? I'm getting ahead of myself. What should we do next? Other than the Kiel, John.
Specialized theta L.
Okay, very good. I'm going to put that specialization here. Specialize A to L to what value of epsilon? Over 2. Okay, then I need a proof that that's positive. So let's call that have, I don't know, delta. I don't know, F1. F1 is a proof that epsilon times L squared over 2 is positive. That's going to need one more fact, namely that L is positive in absolute value. So maybe this is have F0, that L is positive in absolute value. We know that because L is not 0. And this will be by apply abs pos of non-zero. Abs pos of non-zero, which needs the fact that it's non-zero, which is L any 0. Okay, let me slide this over so I'm not so scrunched. All right, and then it knows the positivity of epsilon, knows the positivity of L, so it knows the positivity of L squared. This should just be by bound. And then I should be able to just call F1. Now, once I do that, remember, what does A to L now look like? Yeah, there exists an n, so that for all n greater than n, an minus L is at most epsilon L squared over 2. There's a problem. Once we've specialized A to L, we're not going to be able to get this eventuality. The eventuality also takes as an input the fact that A goes to L. So we need to, before we do this specialization, maybe just before, if you like, let's do a have. I'm going to call this F-1, F0 prime. F0 prime is that there exists an n, so that for all n greater than n, an is at least absolute value of L over 2. And what was that theorem called? I don't know, eventually greater than something, eventually greater than or equal to, and then we'll figure out what. This probably needs a sequence, A. It probably needs a limit, L. It probably needs the fact that the sequence goes to that limit. That's called A to L. And it probably needs the fact that L is not 0, which is L any 0. Okay, everybody with me? So that's F0. Let me put this over here. Well, I don't need to put it. It's right there. That's what F0 prime is. So we have an F0 prime. We better get that F0 prime before we mess with A to L and destroy the fact that there's a limit. Okay, so now we have these two statements. Everybody comfortable with that? Next. What's the goal at this point?
Choose.
Exactly. We have to choose. The goal, we got our epsilon and epsilon positive. The goal is now says there exists an n. Where are we going to get that capital N? We're going to get it from the worst of these two capital N's. So let's choose those two capital N's. So choose N1, HN1 using, I don't know, A to L first, and choose N2, HN2 using F0 prime. Right? Make sense? And then what do we want to use? N1 plus N2, as usual. The max would be the right thing, but we're going to be sloppy. Let's record. Oh, okay. So now what's the goal state? Yeah, other than John. Is everybody other than Akil? We should all know what the goal state is, unless I've completely lost you. Have I lost you? I'm seeing blank stares. Brennan.
Well, I guess, question, do we
Please.
always need to have like the facts that like N1 is greater than or less than or equal to N2?
We're gonna get that, yes. We're gonna need that for little n. So we need to get a little n first before we can make that statement.
Is it intro then?
Intro, exactly. Thank you. Yes. So the goal at this point, let's record what the goal is here. The goal right now says for all n greater than n1 plus n2, bn minus 1 over L is less than epsilon. Right? That's what the goal says. And so let's intro n hn, and hn says n is greater than or equal to n1 plus n2. We're going to want to apply it to any n that's that large. And this only needs n to be larger than n1, and the other one only needs n larger than oh, this is let me just go ahead and call this n2 and n1 since they're anyway dummy variables. Okay, so now let's do exactly what Brandon suggested. Let's call this have, I don't know, h little n1 maybe is a good name for it, that n is at least n1, that's by bound. And hn2 is that n2 is also a lower bound for n. And now we can specialize A to L even further. Oh, sorry, it's no longer called A to L, it's now called hn1. hn1 to little n, and then it needs a proof that little n is greater than n1, that's hn1, h little n1. So now, let's keep track. hn1 now says, not just for any n, but for this particular n, an minus L is less than epsilon L squared over 2. Yeah? And now let's specialize hn2 with n hn2. And so now hn2 says what? Exactly. This is where we're sticking in little n and the fact that little n is greater than n2. So it says that absolute value of an is at least, let's write it the proper way, which is the other way around, only using less than signs if possible, an, and that's it. Okay, that makes sense?
Why?
Remember how rewrite goes left to right, but if you want it to go the other way, you put the backwards arrow? So in the same way, like less than signs versus greater than signs, you have two different statements. And so here there's actually a canonical way to just always state it in the same way. So if you just always state it in the same way, you never have to worry about backwards or forwards. Just there are no greater than signs. There's only less than signs. I mean, greater than signs are useful for statements like these, which are they secretly say for all n, comma, if n is greater than or equal to n2, then something happens. So this is where a greater than sign is useful because it lets you give that dummy variable a name. But otherwise, never use, if you're actually arguing something and not introducing a variable, try not to use greater than signs. Okay, so that's what hn2 says. The goal, again, now we've done the intro, so the goal is this. Let's get rid of that b, convert the b. Let's rewrite the b into an a. The way I've been teaching it to you guys is to specialize, but maybe it's time to learn the faster way to do it, which is just to rewrite directly. Rewrite b inv a. And it does, it wants a variable, but it can figure out what variable on its own. So you don't even have to say little n. I'm going to try to speed up our workflow a little bit. Okay, it's the same thing as specialize b in a to n and then rewrite this fact. You can actually do it without the specialization. Right, because it's going to say, it's going to try to pattern match, and it's going to say, do I have a b of something here? Oh, I have a b of n, so I'll apply it to b of n. It'll do it for you under the hood. If it makes you feel better, put the n, but it can do it without. Okay, so now the goal says, let's keep track of the goal, because we're going to need these two facts, and the goal is 1 over an minus 1 over L is less than epsilon. Now comes our big computation. And it's going to be the same computation as what we worked through down here. All right. So the computation, let's call this have F1. Do we already have an F1? It doesn't matter, actually. If we had an F1, we can kill the old F1 and make a new F1. We did. We don't need that F1 anymore. Anyway, whatever. I'll call it F2, which is that the absolute value of 1 over an minus 1 over L is equal to what? If I cross multiply, it's L minus an over an times L. And try not to do too much at once. So why should it know this? It should know this by field simp. It might need a ring afterwards or a bound afterwards. It should just be a matter of field simplification. In fact, maybe to help it do it with the field simplification, we don't need to put the absolute values. What's the they're not doing anything. Maybe we'll rewrite by this fact or something. I haven't decided yet what to do. The one issue is we do know that L is non-zero. Is it going to be able to figure out that A is non-zero? So let's help it a little bit. Let's help it. We know that an is at least L over 2, and we know that L is positive. So let's give it a preliminary. No, don't do that. Give me the pen. Thank you. Let's give it a preliminary have about abs A, which is that 0 is less than absolute value of an. And the reason that's true is by Linnerith. Bound would probably do it, but let me be more precise. Linnerith, I need the fact that an is bounded by this, that's hn2. And I need the fact that L is bounded below, what did we call that? F0. Okay, so now we know that A is non-zero, and just in case it needs a little more help, because there's not an absolute value of A here, there's just an A. And I don't know if A is positive or negative. Let's record that ANE0, which is that AN is not equal to 0. And I think that's a new theorem that I have to give you because it didn't see through it. Let's see, what are the new theorems here? Yeah. One new theorem is abs div. I think we discussed that last time. And the other one is we have abs pos of non-zero. This is non-zero of abs pos. Of course, if the absolute value is positive, that's true if and only if the value itself is non-zero. So this is by apply non-zero of abs pos. And where do we prove that the abs is positive? That's called abs A. Okay, so I think with these two things preceding this equality, field simp should do it. Are you building a model in your head for how to do these kinds of things? All right. So now what? Well, maybe we want to rewrite this F2 into the goal, just so that we, let's rewrite by F2. And so the goal now looks like this. What does it look like? It looks like L minus an over an times L is less than epsilon. That's what we have to prove. That's not what we have. That's what we have to prove. Everybody following along? Okay. Let's break those absolute values down. So let's have maybe an F3, which is that the absolute L minus an over an minus L is equal to L minus an over an times L. And that's by what? Abs div. So apply abs div. Abs div. The fact that we know any of these theorems is the weakness of the tactics as they currently exist. This should just, there should be a tactic called obvious, obvious, obvious. None of this, I shouldn't have to spell any of this out for you. Let's do a have, not a fav, but a have. F4. What? I guess I should break this absolute value up. Absolute value of an times L should be absolute value of an times absolute value of L. What's that by? Absmol. Okay, and maybe if we rewrite this into here and then this into the goal, so maybe let's rewrite F4 at F3. That'll put this into the denominator, and then let's rewrite F3 into the goal. The reason I'm rewriting and not doing any kind of linear arithmetic is because it's not linear arithmetic. There's stuff from the denominator that's changing. So it's not just going to be able to chain it. Does that make sense? So if I rewrite F3, what's the new goal? So F4 got rewritten at F3. F3 used to say this. The denominator got changed to this. And now here's the whole thing, Jeffrey. Perfect. Okay, that's our goal right now. Okay, let's do one more thing, or maybe a couple more things. We have an an minus L. So let's have an F5. Yeah, this gets tedious. I agree. I feel your pain. L minus an is equal to negative an minus L. That's by ring. Then have F6 is that negative an minus L has the same absolute value as an minus L. That's by apply abs neg. Okay. And now what? So now we can say, I mean, you want to rewrite this? Sure, let's rewrite F6. Let's rewrite F6 into the goal. Okay, so the new goal.
You have to.
Whoops, sorry, I have to rewrite F5 and then F6. F5 and then F6. If I rewrite by F5, I get this. If I rewrite by F6, I get that. Yeah. So the goal is now an minus L over an times L is less than epsilon. Okay, we're almost there. Let's have F7, which is that an minus L over an times L is less than, is strictly less than. What do we know an minus L is bounded by? Yeah, exactly. Epsilon absolute value of L squared over 2, and then divided by an times L. Okay, maybe we want to group this as one thing and then this division. And that should be doable by bound. And then how about this last thing? Let's have an F8, which is that epsilon norm L squared over 2 divided by an times L. That's equal to, I just want to cancel the L on top and bottom. Let's simplify this a little bit. Epsilon over 2 an with an L on top. Does that look right? That should be by, I'm going to say field simp. Maybe field simp followed by bound. Again, we're going to figure out, like, if you got this order wrong, but the have statements. Oh, that was another thing. Sometimes you guys are making naked calls to field simp or have, or, field simp or bound or things like this. Always use a have statement so that I know what you think the thing is going to do. Even if it doesn't do, even if like it was field simp and ring and not field simp and bound, as long as I know what you were trying to do and I can say, oh yeah, there was some other tactic that you should have used to do that, I can follow your logic. Whereas if you just say field simp right here out of nowhere, and in your mind the goal is changed to something, but I don't know what that something is, that doesn't help. Okay, Daniel, can you put that away, please? Yeah, turn it off and put it in your backpack. Thanks. Okay, so this is where we are with F8. And finally, I think this is it, have F9. I think we should be able to now prove that epsilon L over 2 AN is actually less than epsilon. Maybe less than or equal to, actually, because we said AN is at least L over 2. And that should be by field simp and maybe something else, maybe not. Jeffrey.
For F8 and F9, could you also prove it by like, whatever, I don't know the one earlier, but
By linearith of what?
like, wherever you define it to be less than epsilon, that's about it elsewhere.
Where was it? The problem is it's in the denominator. Yeah, we have this HN1. There's stuff in the denominator, and this is also in the denominator. So it's not going to be so easy. But if we do field simp first, so that's what I'm hoping, is that, well, here, once we do field simp, we probably need bound by field simp and then bound. And then bound should be able to see there's an epsilon there. They're positive. There's an L there. There's a L over 2. The AN moves to the side. I'm optimistic about this, too.
Wouldn't it have been like faster to field simp all the way like back there and literally?
Yeah, it's possible that at this point, it would have been good to field simp. The problem is that would be a naked call to field simp. In other words, we haven't learned the suffices tactic. There is a tactic that says it would suffice to prove this thing if we could cross multiply. I'm still figuring out what the right way to do this, that, you know, given that the tactics are what they are. Again, a future version of this course will have, you won't suffer this much. I understand and appreciate that this is suffering. I'm hoping that it'll pay off. So let me move so that it does. And finally, we're done, right? Because this was equal to that, that was equal to that, that was equal to that, that was already in the goal. The goal was to prove that that's less than epsilon. We have a strict less than sign there and a less than or equal to sign here. So now it should just be linearith. It's linear arithmetic on just F7, F8, and F9. Okay? Let's do it. Any questions? Let's see if the game agrees. Okay. What do we think is the first step? It's intro. Intro, epsilon, H epsilon. All right, we got our epsilon. Now we're going to have this F0, have F0, which is 0 is a lower bound for L, and that's by apply, what's it called? I wrote it there, abs pos of non-neg. Oops. First of all, it's non-zero. Second of all, I have to tell it that it's non-zero, L any 0. Okay, there we go. You guys can see that? Okay, that was F1, that was F0. Let's have F1. F1 is that epsilon times absolute value of L squared over 2 is also positive and bound to take care of that for us. Very nice. Let's have this F0 prime. We have to have that first, which is that there exists, I guess I called it an N2, so that for all n greater than or equal to N2, yeah, the right way to say it is absolute value of L over 2 is less than or equal to AN, and that's by apply. And what is this theorem actually called? Does anybody remember? Here it is. Eventually greater than or equal to half lim. Eventually greater than or equal to half lim. And what do I have to feed it? I have to feed it let's see, can I click on it? Half limb pause, thank you. Okay. All right, right. And there's a reason that why I put a pause there, because there's a homework problem. So it tells you what you have to feed it. You have to feed it the A, you have to feed it the limit L, you have to feed it the fact that A goes to L, which is why we didn't destroy A to L yet. We have to feed it the L is not equal to 0, and then we're going to get what we want. Beautiful. Go away and shrink down. Okay. Now we have that, we're ready to specialize. Specialize A to L, where instead of epsilon, we're going to use epsilon times absolute value of L squared over 2, and then F1 for the proof. So far, so good. Choose N1, HN1 using A to L. Choose N2, HN2 using F0 prime. All right, we've got our N1 and N2. Now let's use N1 plus N2 and intro and HN. Everybody's there? Any questions? I'm going quickly because I think we understand how to do this. Please stop me if anything's not clear. We need new versions of HN1, of HN rather. First of all, that N1 is less than or equal to N by bound. Then we need that N2 is less than or equal to N, again by bound. What's with the cursor? Okay, everything's good. Now we're going to specialize HN1 to N with little HN1, specialize HN2 to N and little HN2. Okay, so now we have our AN. Let's check our understanding. AN minus L is less than epsilon L squared over 2, and L over 2 is less than AN. Great. Everything's moving along exactly as we want. Now, watch this. I'm just going to rewrite B inv A, and it's going to look for a B, and it's going to find a B, and it'll realize that it needs to apply it to B equals N. Rewrite B inv A. Boom. Okay, so there was a pedagogical reason to specialize and rewrite, but now I think we're past that. I think that point has been made. Okay. This is our goal. This is as far as we got. And these are the two key inequalities we're going to use. Now let's get going. Before this F2, let's record that the absolute value of A is positive. So have abs A, which is AN is positive. That's by linear arithmetic using HN2 and F0. Let's just see. F0 is that L is positive. HN2 is that L over 2 is a lower bound for AN. So that it's definitely linear arithmetic, and we got it. And now let's have A not equal to 0 of AN not equal to 0. And that's by apply. Here's this other theorem, non-zero of abs pos. And the abs pos is abs. Oops, I think I meant to call that abs A, but too late. Okay, so now we know the non-zero-ness. And now we're going to make this F2. Have F2, which is at 1 over AN minus 1 over L. And hopefully it'll accept that. We'll find out in a second. L minus AN over AN times L. And that's by field simp, please. Yes. Okay. We got it. And now let's rewrite by F2. Okay, the goal is L minus AN over AN times L is less than epsilon. We're making good progress. Let's have F3, which is that this thing is the same thing, except with absolute values. And that's by apply abs div, which again, you should not know the name of that theorem. And then let's have F4, which is that the bottom, come on. Just want to grab this bottom. So I think I'm not saving myself any keystrokes at this point. I have to rewrite everything. AN times absolute value of L. And that's by apply abs mul. Okay, then we said we would rewrite F4 at F3. Rewrite F4 at F3. And then we would rewrite F3 at the goal. But rewrite F3. Okay, so now we've broken up, it took that much work to break up the numerator and denominator. Okay, let's work on the numerator. Have F5 that the numerator, L minus AN, is equal to negative AN minus L. That's by ring. And then negative AN minus L, have F6, which is that negative AN minus L is the same thing without the minus sign. That's by apply abs neg. And now we said we would rewrite both of those. Rewrite F5 followed by F6 into the goal. Suhas. Okay, if I field simp at the goal, and again, I don't like naked field simps because I don't know what it's actually going to do. It did the cross multiplication. It's possible. It's possible that this should now know enough between HN2 and what's it called? HN1, I guess. No. Because it's not linear. It's not linear. You're multiplying two things. There's a tactic that we don't have called n-linearith, yeah, well, the tactic's not available in this game, of course. There's non-linear linearith, so non-linear arithmetic, yeah. Okay, so where are we? Yeah, so we're gonna not do the field simp. We're almost there. It's true that the field simp would save us a couple of lines. Let's see, I wrote the F5 and F6 already. Yes, so we're at F7. We're close, guys. Let's finish it. What's that? Sorry, Jeffrey?
But if you did do the field simp, you could definitely say like something is less than the left side and right side is less than something else.
Yeah, maybe bound would do it. You want to see if bound would do it? That's the turning it off?
Yes.
Like, come on. Okay, so we're going to very soon stop doing explicit examples. The explicit examples of like the inverse function or multiplication, these explicit examples are painful. And the more abstract, there's a much better theorem than the theorems we're proving now. It's just that we haven't built up the technology yet to state and prove those theorems. And you'll see that it will go better. I keep promising you it's going to go better. And I better at some point actually make good on that promise. Okay, let's just plow through. AN minus L. It's not seeing that the denominator, it's not seeing all kinds of things. Less than, I'm going to replace AN minus L by epsilon times L squared over 2, because that's what the numerator is bounded by, and I'm not going to do anything to the denominator. I'm going to try to do as little at a time as possible, and that should be true by bound. What did I do? Thank you. I try to always put spaces anyway, and I for some reason didn't there. Okay, so that's that bound. And now let's do F8. F8 is that this left-hand side, that's an equality. Equalities are somehow much easier than inequalities. So I'm just going to kill one L on top and bottom. And I'm going to clean up this 2 into division. And that should just be by field simp, please. Maybe. Oh, yeah, and a call to bound because oh, no goals need to be solved because field simp already did it. Fine. I didn't need that trailing bound. Field simp already cleared it. Whoops, I called it F8. So there, if you call something, if you make a new fact, it must think I did it twice. So let me retry this and just get rid of the bound there. This is a bug in the game. Okay, there we go. Great, we're almost there. Have F9. F9 is the fact that epsilon times absolute value of L divided by 2 times AN is less than or equal to epsilon. And that now I think will need both field simp to cross multiply and bound to call the hypotheses. And now we're done. Now it's linear arithmetic. If I start with F7, which is the left-hand side of the goal, and I replace this by the right-hand side, that's F8, and then I use the bound in F9, that's everybody. Okay, moving on. I realize it's far from perfect. We're gonna keep moving. All right. I have to teach you a new thing. We already know that if you already have a hypothesis H, which is P or Q, then you write cases prime H with HP, HQ. What if you want to break into cases, but you don't already have a hypothesis to play with? So that's called where is it? ByCases right here. I guess it crashed already. So the ByCases tactic, the syntax for ByCases is ByCases, you give the name, your favorite name for a fact, and then you state what that fact is. So let's do a simple example. Here's our simple example. I'm just going to clear it. Okay, our objects are a sequence A, a real number L. I skipped straight past step 3, part C. Now that we have the proof in formal language and we check that the formal proof actually works, let's give a natural language proof. And maybe I'll do it in text, okay? So that you can actually read my handwriting. Part C, natural language proof. Okay? Everybody remember what we're trying to prove? That proof that 1 over AN, that 1 over AN goes to 1 over L. The problem is I don't have, in here, I don't have all my hotkeys and stuff. Okay, proof. Let epsilon be given, and assume epsilon is bigger than 0. Then epsilon times L squared, absolute value of L squared over 2 is also positive. No need to justify that, it's obvious. Okay, and we know that L is not equal to, how do I do not equals? I guess that's going to be not equals. Not equals to 0. All right, so that's obvious. Since AN goes to L, we can make little n large enough so that AN minus L is less than this epsilon L squared over 2. Okay, we don't have to be explicit about this N1, N2. We can also make n even larger if necessary, so that AN is at least L over 2. Okay, so taking n that large, I'm trying not to write it by just saying choose and use and applying and calling all the formal names, but the formal names are just more precise. It's just better. I hope you're starting to appreciate that it's just better. Like, this is so wishy-washy compared to what we can do formally. We also can't see the whole thing. How's that? A little better. We can also make n even larger so that AN is at least L over 2. Taking n that large, we can bound. Okay, so 1 over AN minus 1 over L is equal to L minus AN for the numerator an times L for the denominator, which is strictly less than, now I'm going to use the numerator bound, epsilon, Daniel?
I don't know which way, which end. Like the n such that a that or the a greater than that. To wrote it as like one is clearly larger than the other.
Well, taking n large enough for both conditions to hold, if you like. Right?
No, I thought
I
like
think he's talking
I-
about even larger.
Yeah,
or
yeah, yeah.
before.
you can say if I think you said if
I-
needed.
If needed, yeah, if need be.
No, I thought you said I thought this was like a true statement that one is larger than the other.
No. If you need to take it even large, at some point, eventually, after a certain point, this is always true.
Mhm.
And eventually, after a certain point, this is always true. So just take it large, large enough so both of them are true. So that's the choose N1, choose N2, use the max of N1 and N2, or even better, the sum of N1 and N2. Intro NHN. Okay, hopefully you're seeing. I don't know why I'm still trying to write this the way you see it in books. It's just bad the way it's written in books, as far as I'm concerned. All right, I'm bounding the numerator by epsilon L1 L squared over 2. The denominator stays the same over, well, in fact, in one fell swoop, I can leave that L and the denominator is at least L over 2. So 1 over that is at most times absolute value of L over 2, which is equal to epsilon. Done. Very wishy-washy. I don't like it, but it is the way that this would be a perfect solution in a normal real analysis course. Okay. So I just took the numerator, replaced it by its upper bound. I took the denominator, replaced it by its lower bound, and that of course gives an upper bound. And then it's just the L, we have an L squared on top, L squared on bottom, 2 on top, 2 on bottom in the denominator. And I think I'm missing, this parenthesis is not right. Lean wouldn't let you make a parenthesis error. Okay, this is supposed to be in the denominator. That's it. Okay, I want to make sure we do part C. All right, moving on. So now, where were we? We now want to prove this theorem, which looks just like the theorem we proved. We proved eventually greater than or equal to half lim, as long as we have the extra condition that L is not equal to 0. But as we discussed last time, it's true whether L is equal to 0 or not. So let's break the proof into cases according to whether L is 0 or not. Okay, and that's called ByCases. And let's give that a hypothesis a name, HL. And it's whether L is 0 or not. Okay, so this is the command, that's the syntax. ByCases, the name of the hypothesis, the new hypothesis, and then what the hypothesis should be. So now when I hit enter, we are going to have 2 goals, an active goal and a goal that we'll have to come back to later, 2 sub-goals. The first sub-goal says L is equal to 0, and the second sub-goal says L is not equal to 0. Okay.
2 questions. One is, I don't know if this, is there a way to split up like an and with the hypothesis?
In the hypothesis,
Like if I have a like an assumption that's like an and split.
Yep.
What's that?
that's the dot product, the dot notation. H.1 will give you the first part of the and, H.2 will give you the second part.
You can also use a have to.
You
Yeah,
can,
that's
you,
I tried like specializing at 1/2 of the thing.
oh, no, you can't specialize at 1/2 of an and. Well, you can, but it's more complicated. Yeah, it's better if you just want to isolate that statement by itself, you just say have the name and then what that statement is, and by apply hypothesis.1. Now you have isolated .1. Yeah. Okay. So this is the case that L is equal to 0. How are we going to be able to prove this theorem? Yeah, any value of n, we're trying to show that absolute value of an is greater than or equal to 0. So there's nothing to do. Use 42 or something, 67, and then intro NHN. I think my kids are closer in age to you guys than to me, so that's why okay, so then what's the point? Now we know that L is equal to 0, so just rewrite that. The fact that L is equal to 0. And now our goal is to show that AN is bounded by that. I think I don't have to do anything. Bound will just do it. Okay. The intermediate goal is solved. Now we're here. And we know that L is non-zero. There's nothing to prove. We already proved this. Let's just quote it. So apply the theorem that was called, what was it called? Eventually greater than or equal to half limit pos. I think it shouldn't be pos, but NE, but whatever, too late now.
Not let them rewrite it L. So, or that one.
Say that again. Do we not need to split?
Like, will the take not L equals 0 instead of L not take?
Not L equals 0 and L is not equal to 0. It should always be able to convert between those two. Those two are, are definitionally equal. Eventually, greater than or equal to half lim pos, which wants, can I hover over it? Can I hover? Oh, I can. Look at that. Nice. If I hover over it, it tells me what it wants. It wants an A, then an L, then the fact that it converges, then the fact that L is not equal to 0, and then we get exactly what we want. So it wants an L, an A and L, the fact that A goes to L, and the fact that L is not equal to 0. Eventually. What's wrong with eventually? Okay. So now we know how to split things into cases. Any questions? Okay.
Like the midterm, would like the argument of these theorems be given?
Yeah. I'll always, just like before, I told you what the theorems said and yeah. Well, the ones that we prove, you should know the theorem. You should know the statements.
Yeah, just like the order.
The order of the arguments. If you get the order of the arguments wrong in your formal proof, I don't care. Right? This is not something I want you to memorize. You should know what the theorem says, and you should know the kinds of things it needs as inputs. But yeah, not something to worry about. Okay, any questions? So that was the last, the tail end. We left one thing and then I added one little appendix. Let's go to what we wanted to do today, and let's talk about induction. You guys have seen proofs by induction in 300, yes? So we know the basic principle, the gist of induction. So here's a theorem. This is actually not entirely trivial theorem. Let's prove it on paper first, which is that if n is a natural number, then n is strictly less than 2 to the n. Okay? Let's make this our quiz. So you have 1 minute to try to write out. So quiz, prove by induction that for any natural number, n is strictly less than 2 to the n. Just as a natural language. 0 is a natural number. 0 is a natural number, and let's check that this works for 0. 0 is strictly less than 2 to the 0. Yes, it is. Is this too hard of for a quiz? No, okay.
You need to be like formal, like the stats.
Do your best. It's just a quiz, right? Doesn't matter. Write what you think you need to write to convince yourself that you would be able to do this design. And the hint was use induction. And also talk to your neighbor. in the interest of time, let's talk about it, kind of keep working, but let's talk about it together as well. What's the first thing you're gonna do? Yeah, let's argue by induction. Argue by induction. Okay, so the base case is n equals 0. So we have to show that 0 is less than 2 to the 0. 2 to the 0 is 1. Norm num. Let's get our scratch work. Scratch work for induction. Okay, so we assume the version of induction that we'll see here is not that it's true for n minus 1, but that it's true for n, and then we have to prove it for n plus 1. Okay, so assume that n is strictly less than 2n plus 1. That's our hypothesis. Let's call that hn or something. And our goal is to show that n plus 1 is less than 2 to the n plus 1. This should be pretty easy. There's a little catch to it. So how are you thinking about this? You know, adding 1 should surely be less than multiplying by 2 or something. But actually so really what you want to do is something like n plus 1 is less than 2n. And n is, by the induction hypothesis, n is 2 to the n. And then this is 2 to the n plus 1. Right? That's all that has to happen. There's only one problem with this. Okay. This is not true. It's true unless n is 0. N is 0. So we have two cases. Even in the induction step, we have two cases. So let's split this by cases on whether n is equal to 0 or not. If n is equal to 0, so the first case is that n is equal to 0, then I'm looking at 0 plus 1 is less than 2 to the 0 plus 1. And that's even easier to prove than, well, they're the same. It's just norm num again. Right? 1 is strictly less than 2. And otherwise, we need something that says n is not equal to 0 implies actually n is at least 1. And if n is at least 1, then you can show this just by linear arithmetic. And then by the induction hypothesis, you get this, and then you're done. Okay, Roger.
You could split the case without, like, you could avoid the case of you just make like n plus 1 is less or equal to 2 to n.
Sure.
And you get that because like they're both n and 2 are both integers. So
Yeah, but I want to prove a stronger here. Not that n is less than or equal to 2 to the n, but n is strictly less than 2 to the n.
yeah, but like for induction,
Just add
because
one
2 to the
both
n is
sides.
smaller than 2 to the n plus 1.
Sorry, say it again. Let me write down what you're saying.
So like first is n plus 1 is less or equal to 2 to the n. And then you have 2 to the
Okay.
n is smaller.
You're saying just use induction. You're saying because we have this and because they're natural numbers, then this actually implies this. Clever. I like it. I wanted this as an excuse to use ByCases, which we had just learned. But you're absolutely right there that this should within the natural numbers imply this. We'd have to see which tactic lets us do that, Jeffrey.
I think even if you don't, first, if you just add 1 to both sides,
Yeah.
you get n plus 1 is less than n plus 1.
Yes.
And then, so since n is not negative, then the 1 on the right side is less than or equal to 2 to the n.
Okay. And 1 is less than or equal to 2 to the n. Yeah, that's another way of doing it. All right, fine. We don't have to use ByCases if you don't want.
I just don't wait, but I'm worried, doesn't that have like the implicit assumption that 2 to the n of all those cases? Like that's like a separate thing that
You mean this?
yeah. Like that feels like a separate thing we need to prove by induction. Yeah.
Yeah, well, that fact would need a proof. You're absolutely right. Yeah, we don't have access to that fact with anything that we, it's too hot than I meant.
Yeah.
Very good.
I did the last way as well, but instead of proving the one is less than equal to two raised to n, it just show that one is less than equal to two raised to n when n is zero. And then say that e to the n is a growing function by taking the.
Okay, but that's a lot more, yeah, so all of those things are correct and good in natural language, and if we actually want to formally establish something like this, I think the fastest way is by cases, which is why I went that way. Okay, let's do it real quick while you guys hand in, well, you can hand them in at the end. Let's do it real quick, and then I guess that's as far as we'll get today. So, we're gonna do this by induction. So remember the syntax, which I have here for you. Induction, again, it should be called induction, but there's technical reasons why it's called induction prime, n with, and then you can give a dummy name for what the variable is that you're going to induct on. I just stay with the same variable name, and then the hypothesis, induction hypothesis. Okay, so induction prime, n with nhn. All right, we have two goals. The first goal is that 0 is less than 2 to the 0, and then the second goal has the induction hypothesis, and then this goal. So that's because of norm num, just numerical evaluation done. This one we're going to break by cases on H, I'll just call it H, which is whether n is equal to 0 or not. If n is equal to 0, then rewrite the fact that n is equal to 0 and norm num. And if n is not equal to 0, well, then we have a fact, let's call it F1, that n is at least 1. And this is where we needed a new theorem name because none of the tactics that I wanted did it for us. It's called greater than or equal to 1 of non-zero. By apply, greater than or equal to 1 of non-zero, and the non-zero-ness is H. Okay, so now we have 1 is less than n, so now let's have F2 that, where was it? We're right here, we're right there, that n plus 1 is less than or equal to 2n, and that will now go by bound. Very good. And now, can I just chain the induction hypothesis? I guess I have to do one more thing. Will bound just do it? No, it won't. Okay, good to know. Like, it knows that n plus 1 is less than or equal to 2 to the n, and it knows that n is strictly less than 2 to the n, and it can't put the 2 and the 2 to the n together to make a 2 to the n plus 1. Extremely frustrating. Field simp?
Like, would that split up the two?
We might have to, maybe if we split up the 2 to the n plus 1 first. Yeah, that's exactly what I'm doing. 2 to the n plus 1 is that times 2, and that's by ring. Okay, and now let me rewrite F3. And maybe now bound will do it. Yes. So it couldn't split. So, okay, there's still annoying stuff like this. The point was, now you know how to do induction. It's induction prime on what variable you want to induct over with, and then a bound. Daniel.
What do I do with basic case other than?
You cannot, okay, so that's what the induction, there's a fancy induction that's very powerful, and I don't like its syntax. And we will only ever use a much more basic induction, which will not be fancy. All right,